Okay, Astro 7 students, we are going to do a related presentation now to the prior one, which was on ice and ice changes due to current climate change. This is on sea level rise, and of course when you melt ice you're going to raise sea level. So there is going to be some overlap, and this is a shorter show. I keep meaning to integrate these two together into a single one, but I haven't done it yet. So in the interest of being able to just keep the flow going, I'm just going to go ahead and do this one now, and then I can put this up on YouTube and it'll be ready for you for studying for our next quiz. So thermal expansion of warm water is one way in which sea level rises. We talked about that last time. The second and only other way that you can raise sea level is with the melting of continental or so-called permanent ice. So we're talking about glaciers, we're talking about the ice caps at Greenland and Antarctica. In the past, about half of the rise in sea level that we've seen in the last 100 years, roughly about 8 or 9 inches, has come from just the thermal expansion of warm water. And only now is the melting of continental ice contributing about half, or actually a little more than half, of what we see. And of course going forward that's going to dominate. So sea level rise is averaged about 1.8 millimeters a year over the last 100 years, but it's now almost double that. In fact, I think it is more than that. This slideshow needs to be updated to the last data. I think 3.5 millimeters a year was the last I remember reading, and that was even a year or two ago, so it might be higher now. But anyway, it's roughly doubled since the over the average of the past century. So we are seeing accelerating rise of sea level, and it's caused by both, but mostly by the melting now of continental ice. And this graph's a little complicated. I don't want to spend a whole lot of time on it, but what I want you to notice is that the brown, which is the observations, are virtually always far to the right of what the predictions were. So the IPCC predictions were wrong. They were too conservative. And this fits with what I've been telling you for quite a while now. The structure of the IPCC is such that you need consensus from not just the scientists but also from the political forces and the overarching ruling UN for anything that is officially published under their official nameplate, as you might describe it. And since a lot of the political people are interested more in pro-growth and not in getting the science exactly right, since those two are definitely at odds, then we're seeing conservatism that the scientists would not agree with, and there's certainly plenty of scientists who have shown that, and we'll see a little more of that later. Okay, but basically, Jeremy Jackson, for example, points out in this seminar, which you can click on, that the IPCC projections of sea level rise are less than half of what reality has shown every time they come out with a new assessment report. Okay, so we saw this before also. Almost all of our greenhouse heating has gone into the oceans, most of that in the upper oceans, but more and more of it is going into the deep ocean. So you see as a fraction, the dark blue here is rising. So back in 1980 it was almost all in the upper oceans, and now we're almost a third of it's gone into the deep oceans. So there is a rising amount that is, not surprising, going into the deeper ocean. And periods of time when that happens more efficiently are also times when the rate of increase of global temperatures has been slowing, as we saw in an earlier show. Only down here at the bottom can you see how much has gone into the land and the atmosphere, and it's tiny by comparison. Another way to see the same thing, maybe it's a little bit clearer, but it's not over time. This is as of the time of this graph, which is a few years ago. Now, in the past, so going up to 2000, the models and the observations agreed with each other reasonably well. But that is getting worse and worse as time goes on, because we're beginning to trigger more nonlinear effects. There's accelerations that are not in the models and certainly not in the projections. Of course, part of that is political. Now, sea level rise shouldn't be thought of like the level in your bathtub. So I'm sure that many of you are tempted to think that sea level is like the level of your bathtub. It's dead flat, but it's not. It's not for many reasons. One of them is that El Niños happen, and El Niños have a lot of warm water over the equatorial Pacific. Warm water piled up is less dense, and so there'll be and it takes time for that to try and travel elsewhere. And so sea level over months or even a year time scale will vary because of that. Areas that are affected by El Nino, and of course La Nina is on the average the opposite. There's also the height of the so-called geoid. So the geoid is the gravitational potential energy surface of the Earth, the place where if you had no other effects, no rotation, no winds, no nothing that might affect sea level, then that's the surface parallel to where sea level would be. So we call that surface the geoid. However, the geoid is slowly changing with time. For one reason that is going to be very relevant as we go forwards is just the redistribution of ice cap gravity to the ocean itself. So as water goes from a concentrated place like Antarctic ice and then flows into the ocean, where then it can flow everywhere, it lowers the gravity of Antarctica, and that means that water will not be pulled up against the shorelines of Antarctica as much as they were. So we're going to see that paradoxically, when West Antarctica and increasingly East Antarctica melt more and more, sea level rise is actually going to be slightly negative in Antarctica. So that may seem a little weird. So where is sea level going to rise the worst? It's going to rise worst here in North America. And that's again because the gravity of the ice is now missing, because it's now moved to the ocean and flowed long distances away. And then this is a great graph that we have seen before in the previous presentation, and this shows that there's a pretty linear trend, at least up to 1992 through 2014, of sea level rise. But there's ups and downs, you see. So these circles and dots and so forth, they do have more accuracy than can be accounted for by the straight lines. The straight line's the best fit, but there's definitely ups and downs happening here. We talked about this one as well. So this was a time when we had extraordinary rains going on around the world, and that basically takes water from the ocean and dumps it on the land, and it dumps it on the land perhaps far inland, like over the Amazon basin or over the Andes and in Africa, and it takes a while. It can take a whole year for that water to slowly work its way back through the groundwater and the streams and then to the rivers and then eventually back to the ocean. And so you really have to draw a good straight line here if you want to see the long-term trend. And the long-term trend is relentless. Sea level is rising. Climate denialists tried to make a big deal about this. Look, everything's changing. It's all different. Look, everything's fine. Go back to what we were doing. CO2 is not a problem. And then, they're kind of like spiders, these guys. They go crawl back under their rocks, into their old wood piles until the next opportunity is presented where they can jump on something. But this whole thing was debunked pretty quickly, and at least we don't seem to hear it anymore. Okay. So this was an interesting study by Hai et al., and they showed that, in fact, the earlier data pre-satellite had a poorer calibration to it than we appreciated, and that sea levels were actually higher than were thought. So what that means, let's look at the graph. So our better idea for sea level now is more like up here. So in one sense you might say, oh, well, look, hey, things weren't as bad as we thought. But no, this is actually not a good thing. Because if what we had thought was this, it makes a more constant rise in sea level. But now you see what the truth is that we have a rapid acceleration going on right after the temperature period that we talked about before, that was dominated both by smog and by the Pacific Decadal Oscillation being in its low phase, that inhibited temperature rise for about 30 years. And that ended about 1980, and since then sea level has been rising at a clearly more accelerating rate. So this actually fits a lot better with the temperature data than the old sea level data back here. So actually nobody is really surprised by this now. So again, it shows higher acceleration rates during the global warming era than earlier data thought. So how does today's sea level rise compared to the last 8,000 or 9,000 years when we've been in the regime so-called the Holocene? And you can see why civilization was able to prosper and to grow so efficiently beginning at the end of the last ice age, and that is because sea level was constant, and we could build our cities on the coastlines and depend on those coastlines to be the same coastlines that we would have century after century for thousands of years. And so we've got most of the great cities of the earth originally starting out as ports and now evolving into huge cities because we've had that constancy. We've known where to put our croplands. We've known where to build our cities. We've known which rivers are the rivers to build next to. We've had constancy, and that's essential if you want to have an efficient growth in civilization. And now you can see we're transitioning out of that, and this is the rate of sea level rise as of, let's see, this is 1993 to 2003, so even this is a little lower than we have today here in 2020. And so why is it rising and going up at an accelerating rate? So we looked at this last time, and it's becoming mostly due to ice loss from Greenland and from West Antarctica. So here's Greenland's loss in ice in billions of tons, gigatons. That's a gigaton is a billion tons. And this is just the last 10 years from 2003 to 2013. The acceleration is pretty obvious. And here's another graph, and this one's interesting because this data point up here, while it does have error bars, at least nominally it is slightly above zero. In other words, Greenland was actually gaining ice for a while. And that was during the late 70s and perhaps into the early part of the 80s. And this could be attributed to rising warmth causing higher humidities and therefore higher snowfall on the parts of Greenland that were high enough that that precipitation all still fell as snow and remained as snow and didn't melt very much. Clearly that regime has ended, and so now we have ice falling rapidly, and this only goes to 2009. So this only goes to 2005, but it's enough to show the accelerating loss in Greenland. I think we saw this graph in the last PowerPoint. And then this shows glacier mass loss worldwide. I think we saw this one as well. Patagonia is the worst. Europe had actually been not too bad for a while, but as of 1992 maybe, it's now joining the rest in accelerated melt. And this is an annual contribution from glacial melt, so this is not taking into account the rise in sea level due to thermal expansion. This is just the ice coming off the glaciers, and clearly that's accelerating. Antarctic ice loss accelerating as well. So the green line is the best fit. So this is the boundary between West Antarctica, which is here, and much higher East Antarctica, which is here. East Antarctica is not expected to suffer much melt in the near future, although there are places in East Antarctica which are expected, and we are seeing more melt. I include Totten Glacier here. But mostly it's West Antarctica, which is lower and therefore more subject to warmer air, thicker air, denser air, and more melting. And if you were to peer beneath the ice here, then you would see ocean bottom. And of course, the warmest parts of Antarctica are up here in the Palmer Peninsula, where the Larsen A ice shelf is already gone, the Larsen B ice shelf is already gone, and the Larsen C ice shelf, much larger, is in breakup. Already a Delaware-sized piece of it has broken off as of about a year or two ago. Not yet broken apart is the huge ice shelves, this one, and then the Ross ice shelf down here. But West Antarctic ice sheet wastes. The Pine Island Glacier, I think we saw this picture before. This is where it terminates into the West Antarctic shallow seas, which are kind of hard to recognize because they're covered with so much ice, but they're going to get easier and easier to recognize. When West Antarctica is completely melted, that will raise global sea levels by about 12 feet. And then we talked about how the West Antarctic ice sheet is now believed to be in irreversible collapse because the shallow ocean basin into which these glaciers are going has a large ridge which has been holding up the gravity-fed glaciers that are going over it. And the melt is happening primarily not from on top of the ice, but from beneath it, where the warm waters are being insulated from the air, where they can hopefully get cold in the winter. They're being insulated by a thin layer of fresh water, which is less dense, melted off of the ice. And so the warm water has a higher tendency then to melt the undersides of the glaciers, and they've actually melted the underside enough of Pine Island Glacier and Thwaites Glacier to unhinge them from the ridge that has been pinning them and keeping them from moving forward. Now they're just floating and much easier to push out into the open ocean. So again, we already talked about that last time, so I'm not going to belabor that too much here. Okay, this we didn't talk about though, and this is important. So a very recent study, just a year old now, by Culp and Strauss, shows that satellite data for the coastal elevations have not been properly corrected for buildings and vegetation that are projecting above ground level. And the average wrong calibration is pretty darn high. It's 1.9 meters. That's about as high as, a reasonably tall adult. And that makes a big difference. So even the relatively conservative sea level rise projections of the IPCC, actually we would now say dramatically conservative sea level rises, the flooding to come will drown far more cities and lead to huge population migrations as they go underwater, and not by 2100 but even by 2050. So additional current populations are newly found to be underwater by 2050 is over 200 million people. So let's talk about that a little bit. So this is not from flawed data on rising sea level. This is actually from flawed data on how high is the coastlands of areas of the world where we didn't have great maps. This isn't such a problem in North America, but it is a problem in Asia. This is where the data was not nearly so good. So here's the old projections for 2050, and there was sea level rise. That's the blue, the newly dark blue areas that projected to be underwater. But now you see by 2050, with the new data, the whole city of Bangkok is projected to be underwater. I've got to hit the control button while I press my mouse key to have you guys see my little red thing. It's a little awkward. But yeah, so all of this is now underwater. And that includes basically the whole city of Alexandria. This is in India, around Mumbai. See, we did have some trouble anticipated, but most of Mumbai was going to be okay. Now, all the inner city, as well as all these other places we already knew about were in danger, they're all going to be underwater. Shanghai, same thing. Now it looks like it's going to be cut off. Vietnam, much of South Vietnam, now projected to be underwater. So that's the companion to my ice changes in the new time of current sea level rise. We have a whole separate presentation I'm going to give a little later on future sea level, future everything really. And so I'm going to end this one now so I can go on to my next one.